The dates that are on Canvas are the 3rd and the 30th.
Yeah.
Homework, all the things are correct?
No.
Oh.
Okay, welcome to thermodynamics. And it has been brought to my attention that I wasn't very careful with my dates. And generally your lab will be due the next lab period and not on Saturday. Like we got something that's due on Saturday, and if you want to come in, slide it under my door. The building will be open. But mostly if you have a lab, it's due the next week. And I try and set up the homework so that we're going to finish talking about a chapter, and then there's at least one class period when if you have questions about homework, you have a chance to ask a question before the homework's due. So that's the intent. And I'm probably going to have to go through and upgrade, because I think what I got was some of the dates from last year, and now it's like 2 days different or something. So anyway, that's I've had a couple questions about that. That one slipped past me. Say again? Yes, because we should be, we're done talking chapter 1. I'm going to wrap up it and then start talking chapter 2. And in theory, tomorrow will be when chapter 1 homework's due. In theory, in practice. Here's a problem.
So it is tomorrow, not the 3rd.
For example, if you have 10 kilograms of CO2, how big of a space would that take up if it was atmospheric pressure at 25 degrees C? One of my criteria is it's going to be a room that's 2.3 meters, which is kind of a weird number, except it's 8 feet is a standard room height. So, basically, how big of a room would fit 10 kilograms of CO2? Just for grins. In order to do that, we're going to need to use property tables. And we're going to talk a little bit about the uncertainty. And in fact, while speaking of uncertainty, your lab's talking about uncertainty. So go over the lab calculations a little bit here first too. Basics on the lab are that there's a quantity of energy it takes to heat up all the water in your lab, and it relates to it's going to take more energy if you have more mass. It's going to take more energy if you have more change in temperature. And there's a material property of how much energy does it take per unit mass per degree to do it. That's the CCP. When you break it down, in order to find out what the mass is, you have the volume flow rate, 2.5 gallons per minute, times the time, 10 minutes, it gets you 25 gallons, times the density, tells you if you got 25 gallons, how much does it weigh? It's going to be about 200 pounds. And that's the mass. And now the CCP is material property. That's a hard number. This one's a hard number, except it varies from the cold temperature and the hot temperature, and it varies between those two, and we're going to pick the number in the middle. That's a relatively hard number. And then the cold temperature is a hard number, but the hot temperature isn't, and it varies a bit. So this range can vary. If this was a 50-degree temperature difference from 54 to 104 degrees, 104 is about a hot tub temperature, and this is plus or minus 1 degree. It's not 1 degree out of 103 degrees. It's 1 degree out of the 50 degrees. That's like a 2% variation. If it's 2 degrees, then out of that it's a 50-degree temperature difference, not 104 degrees, whatever. Now you're talking like 4 plus or minus 4% on that. If it's a 5-degree, it's the temperature difference that matters. That piece of data is what you have a percentage variance on. And likewise, this has some variation. It was plus or minus 20%. This you said it was going to take you some number of minutes, plus or minus half a minute, half a second. I mean, you're going to set the timer every time you take a shower. How many people set their timer every time you take a shower? Not me. I don't even set my timer to wake up in the morning. But there's a variation here, and that's going to be, if you do that in terms of percentages, then you can take, when you're all done with your dollars, this quantity is this one. This dollars per quantity is 6 cents per kilowatt hour. And you end up with dollars. You're going to have kilowatt hour turns into kilojoules, and this is kilojoules. And the units wash out. They cancel like algebra, and you end up with dollars. Well, now how much does it vary? If you have this all set up, you have an expected value that was your Q, expected. That would be your average, the number when you're doing it right down the middle. Well, how much is it going to vary? When you take each one of these in your formula, and this is plus 20% or minus 20%. So I can, for my high value, I could say it's my average value, 1.20. That's my, now I've basically scaled whatever value I put in here before, and I can just say, okay, and if I put in that high value, it'd be 20% higher than this number. You put in the time with the high value. Maybe it was 4% variance on each side. You can say 1.04. Density is not going to change much. So that's a 1 because it didn't change. This property here doesn't change. They will change with a wide enough range of values. But for our purposes, it's a constant. That's a 1. It doesn't change. This one, if it was, you got 50 degrees, plus or minus 2 degrees, you got plus or minus 4%. So on the high side, it would be 1.04. Well, actually, the time was a different percentage. Let's say it was 15%. That was my T. That was my volume flow. My delta T, 1.04 maybe. And that would be a fast way of calculating. And then you put the dollars per. That gets you the high range estimate. And then the low range estimate, you put in the 80.8 for 80% of your standard value, 85.85 for 85% of your standard value, whatever it was, 90.96 for your, and then that gets you your range. You have an expected number, you have a high value, low value. How much does it vary? You could also just put in all your high numbers into here, put in all your low numbers into here, and get your range that way. That works too. But part of the exercise is how much is it really varying? It's not just this number down the middle. In mathematics, everything's precise. You know 2 times 2 equals 4. It's not 4.1 or 3.7. It's 4 with mathematics. But the problem is the numbers we're using with our mathematics are not, they're not solid numbers. There's some give to them. How soft are they? That's why we want to be aware of these things. So that brings us to where we started with all this was the example. And I'll probably be posting, because we're done with chapter 1, after I'm done with this, I'll have these posted on the Canvas site after this afternoon. So the question is, we have 10 kilograms of CO2 in a room that's 2.3 meters tall, just standard residential room height. I want to know how big of a floor area would be filled by that much CO2 at standard atmospheric pressure at 25 degrees C. In order to do that, I So what am I given? I'm given this stuff. I'm going to look at a property at this temperature. What am I looking for? I'm looking for the floor area. Here's my box filled with that much. It's that tall. Mass, my very basic definition of mass, is a volume times a density. And the volume is an area times a height. So area times height times density should give me mass. I know the mass. I know the height. What I'm looking for is the area. So I'm going to reorganize this equation and take all this stuff and put it over here. And area equals mass divided by the height divided by density, or height times density. I know this one. I know that one. This is something, it's a property I can look up. And where do I look it up? In your book. And it so happens, should be on page 1007. Took me a minute to find it there. I'll have it up here. And so here are properties of gases, and carbon dioxide is one of the gases. And we got a bunch of different, this is used in heat transfer, this is used in fluids, the viscosity, that's a heat transfer, that's basically heat transfer. Here's thermodynamics kind of properties. I want a value at 25 degrees C. I have 0 and 50. Oh boy. And you notice there's a difference there. We're halfway in between. I'm going to have to interpolate. I could also use ideal gas law. There's ways to do that. But we'll use the tables. And basically take the average of these two. 9635 plus 6597 divided by 2 should give us 80 something. So anyone have happy fingers going on that one? I can zoom that up for us. (96) 1.9635.
8.116 or 1.811.
Thank you. 1.8116. And that's kilograms per meter cubed. And I'll say that's table A23 interpolated. So we've got 10 kilograms.
So on that equation right there, you have mass equal volume, and then P is density. Is that correct? That's what we just got.
It's a row, yeah.
Okay, and then that's equal. What do you have? The area. What do you have?
So then I just took this equation. Forget that one now. Now what I want to solve for is area. So I'm dividing both sides by h in the row, and the h in the row cancel out here, and they end up the nitrated sides.
Okay, and then h is the height.
That's the height of the room.
Okay.
In meters. If this is in kilograms and this is in kilograms per cubic meter, it should end up in area. Square meters should be our result when we're done. So the formulas you get a standard basic formula, and then you use the algebra to solve the formula. Don't take this and start putting numbers in here. You get confused. Always solve the formula first for what you want, and then put in your numbers. And before you actually crank the numbers, make sure that your units are working out. Because if you redid your formula and you made a mistake on that, your units will tell you. And if you end up with, some set of units upside down, you're canceling them like x's and y's in algebra. If the units work out, then your numbers are going to work out. Don't start cranking numbers and then discover, oh, but the units aren't right, because you're just going to have to crank numbers some more. So we got 2.3 meters,
2.3 times 1 point.
and we got 1.8116 kilograms per meter cubed. Kilograms are going to cancel. This cancels one of those, so we got meters squared ups on the bottom, which makes on the bottom of the bottom is the same as on the top. And we got meters squared, which is area, and that's what we're looking for. So now we can,
2.4.
we got 2.4.
What
Is that right?
I did 2.3 times the bottom, and then I divided the 10 by that result.
Yep.
Okay.
Because and just looking at it, 2.3 times, call it 2 times 2, that's 4. I mean, this is a little less than 2, and that's a little more than 2, and that would be a 4. 10 divided by 4 is about 2.5. And so I would expect it to be in that ballpark. Since the 10 kilograms only has 2 digits of precision, I only expect this to have 2 digits of precision. This also has only 2 digits. This had 4 digits, maybe even, this is more precise than all those things. That's good, but that doesn't drive it. The least precise thing is going to drive how much precision we have. So 2.4 square meters.
Are you going to be on the test when we do scientific notation, things like that? Are you going to be on it about the rules, like a 0 between 2 numbers doesn't count? Like you're going to do all those?
So question on when we come to tests, I'm going to be on about significant digits. Yeah. I'm most concerned about concepts, but some of the details you can, if you're implying that you have parts per billion precision, and really all you could do is cut it with an axe, I'm not buying it. So yeah, if we have more than 3 digits worth of precision as student problem sort of things, or the labs that we do, that's probably not reasonable. I worked for the Fluke company, which made calibration units, and getting parts per million accuracy was like, wow, we got 20 parts per million. Well, that's like you actually do the numbers, it's like 0.02% or something. There wasn't that many. I mean, that's pretty incredible when you can do that kind of precision, and you got to appreciate it when you do it, and not just write down numbers, because your mathematical precision, the mathematics guys, they can get as much precision as they want just by. I mean, it's real in mathematics. Engineering, the numbers you're using here is kind of squishy, so we want to be aware of that. So 2.4 square meters, how big is that? For those of us who are more familiar with square feet, it's 10.764 square feet is 1 square meter. So, yeah, it's at 24, 25. What's that work out to? And we're going to do one more trick with that. 2.4 times 10.76. We don't need to go all the way up here. 25.83. Hold that number. I want square root of it. 5.08. I'm going to call it 5.1. So what did we do? We figured out that a standard room that has a 5-foot square, that 10 kilograms of CO2 would fill that 5 foot. That's something like 5 feet on the floor to top of the room. That's 10 kilograms of CO2. Why does that matter? 1,000 kilograms is a metric ton, so you can take that up by a factor of 100, and that's metric ton of CO2 generated. That's what they base a lot of the measurements for greenhouse gas generation. The renewable energy credits are about a metric ton of CO2 avoided. So that's 100 times bigger would get you a metric ton, so that's like a 2,583 square foot house would house 1 metric ton of CO2. Trying to get context, if that makes any sense. 2,600 square foot house filled with CO2 would be a metric ton worth.
You have 5.1 feet square and then squared again. It's just feet. There's no square.
Feet. Yep. Plain old feet. So, that's how we use the formulas, and we reorganize the formula to suit ourselves, and then put in the numbers, check the units before we run the numbers, come up with a number, and then give it some context. So, that is the end of chapter 1. Notes. Which brings us to a new chapter. So chapter 2, we start talking a little more about thermodynamics in particular, and less about sort of this general thing. A system is, we're going to use the word system here in sort of a specific way. The system is the volume of the steam or the refrigerant, the gas that we're looking at, or the liquid, whatever it is, it's the material itself within the confines of the equipment it's going through. We're differentiate that, the difference between that and the surroundings is everything else. We might be talking about the equipment there too, but most of the time we're just talking about the stuff that's flowing through it for thermodynamics. There is a boundary to the system. That would be the boundary to the fluid we're dealing with. And that boundary can move. And we're like a piston. Let's say we're looking at a piston engine. Well, we get the intake charge, we light it off, now it's an exhaust thing, it's under high temperature, high pressure, pressure increased when we lit it off, and it's pushing a piston, the piston moves. We're still talking about that gas, so the chamber size changed. But that would be an example of a moving boundary. There's some boundaries, whereas, for example, jet engine. The jet's going through the air at, 600 miles an hour, however fast it goes. We might draw the boundary. What we're interested in is the area around the engine. And there's air coming in and there's air going out. That system boundary doesn't move. It travels with the engine, but as far as someone on the plane itself, it looks like it's stationary, but the whole system might be moving because the plane's moving. But we're just watching that boundary around the engine, what goes into it and what comes out of it. That's the reason we're doing this, is we want to know, is there energy coming in and energy going out? Or is there mass coming in and mass going out? Is there air coming in and fuel coming in and then exhaust going out? All that sort of thing. So there's a couple of system types. There's an open system where we have a control volume, and that's the case of the jet engine. we're drawing a boundary and we're just looking at what comes in. The fuel's coming in from a fuel line, air is coming in at however many miles an hour, and it's leaving at another speed. The difference in that speed causes a thrust. The reason it comes out faster, that there's a change in momentum. So that's that. Then there's closed systems. That would be like your combustion chamber in a gasoline engine. We're looking at the same charge of fluid, same molecules, and they're within the system, and that boundary is moving as the piston's moving. What we're looking at there is a fixed number of molecules of whatever it is we're looking at. So those are two definitions. We're going to go through a number of definitions here. So to show the system boundary is one of those things. Property. Characteristics of the system, and then when I'm talking system, I'm talking the fluid in the box, whatever it is. Temperature is a property. Density is a property. Because of the C sub P and C sub V and all that, we have an internal energy as a property. You have enthalpy as a property that we really like. You're going to learn to love enthalpy because it wraps a bunch of stuff together. There's an entropy property that we'll be talking about in a couple chapters that tells us the limits to efficiency and so forth. So there are intensive properties. Temperature and pressure are not necessarily related to the mass of the system, it just is. But there are extensive properties that depend on the extent of the system. So the total mass depends on how much mass you have. The total volume would probably depend on the mass. How much gas you have at a certain density is going to determine what the volume is, or vice versa. The momentum of the system, how much mass. Basically, what it comes down to is if you change the mass and the property changes, or the values change, it's your extensive, you are these properties are based on the extent of the mass, I guess you'd say. How much mass do you have? So we are going to pull a trick. And in order to make those properties that are dependent on mass become more not dependent on mass, we're going to divide them by mass and come up with properties like these specific properties. Density is mass over volume. We've dealt with density. In thermodynamics, we're going to turn that upside down. And we're going to say the volume divided by mass. How much volume per unit mass? Suddenly, then, if we do that, we can define this. Now the volume is per unit mass, and you multiply it times mass. You can scale it up and down, and it's not dependent on the mass. You can look at things on a per unit mass basis, and then find an answer, and then scale it up. If the question was, how much fluid has to run through a system in order to make a 10 gigawatt steam generator? Well, it'd be kind of a hard problem to answer if you don't do this, but if you do this and then you come out with, well, 1 kilogram of steam per kilogram, each kilogram of steam going through the system is going through this process will get us 117 watts. Now, how many times does 117 go into the 10 giga or whatever we had? And we can say, oh, therefore we need, making the numbers up, 2,300 kilograms a second. But now we can scale it. So we're going to deal with a lot of specific properties, and what the specific means is we divided it. It's all going to be volume per unit mass. It's going to be kilojoules per kilogram, and energy, that sort of thing. So we're going to use these a lot. And the first one that you'll run across is just the inverse. It's the same thing as density, only it's upside down. If density is 1,000 kilograms per cubic meter, then specific volume is going to be 0.001 cubic meter per kilogram. That's the same way of saying that same property. So specific volume is literally its density upside down. There's also something called specific gravity that we will use. It's a different concept, but it's specific is about relative to something else. If you do a lot of fluid process things, measuring the content of antifreeze in radiator water, or the charge level of a battery. It's about the density of those fluids. If you make beer and wine, you live and die by your fermentation on this sort of thing. Specific gravity, the density of the fluid you have relative to the density of water. Specific gravity is 1.1. That means this is heavier than that by 10%. It's going to sink, whatever it is. You can also talk about this in terms of solids to tell, is it going to sink or is it going to float? If the specific gravity is more than 1, it's heavier, it will sink. If it's less than 1, it's lighter, it will float. But that's a ratio of densities. We won't use that too much more in thermal. You may hear about that. But specific is always something relative to something else. Specific volume we're going to use. We're going to talk about states. So the state of a system, a combustion chamber, intake stroke, you suck a bunch of air fuel mixture into it and then into a combustion chamber, and then you close the valve. And now that's going to have a certain, at the bottom, pistons at the bottom of the stroke, and the valves are all closed, it's going to have a certain pressure, it'll have a certain temperature, it'll have a certain amount of mass. That's a state. And then if you light it off, it's going to change properties. It's going to stop being air and fuel. It's going to be actually combustion, we'll find out eventually, is taking a hydrocarbon and burning it, and it becomes water, essentially steam, and CO2, and whatever oxygen and nitrogen that didn't get burned will also be part of that soup. So now it's changed temperatures, and it's changed pressures, just because, well, we probably compressed it first, I hope, otherwise it would be pre-ignition. But it comes up, and at the top of the stroke, before we light it off, it's still that air-fuel mixture, but now it's at a higher temperature, a higher pressure, higher density, and that's a state. It has a certain amount of energy to it. We put more work into it, that's what generated the temperature and the pressure from pushing it. Then when you light it off, the piston may not have moved. It's still kind of at the top, but now we've changed the composition, and now it's higher temperature, which gave it a much higher pressure, and now it's going to want to start pushing, but the density changes there because the composition changed. So that's a state. We're going to look at, certain points in time. We're going to define what the state is, and it goes from one state to another. And there's equilibrium. The thermal equilibrium means everything's the same temperature. There could be phase equilibrium, chemical equilibrium. Mechanical equilibrium means all your forces are balanced, essentially. And that equilibrium, even though it's equilibrium, it's equalized, it doesn't mean it's static. For example, a jet engine on a plane, it's down on the getting ready for takeoff, and all of a sudden, they say 1, 2, 3, go, and the guy pulls back on the throttles and everything heats it. Does the engine warm up at that point because you threw a bunch more fuel at it and it's working really hard? You think it's going to be all the same temperatures as it was when it was just idling? It's probably going to start heating up. That's not equilibrium because all the temperatures are changing and it's warming up. But at some point, if you leave the throttle position at the same point, all the thermal masses of the engine will come up to their steady state, and then you'll have an equilibrium. Even though the air is blowing through there at as fast as it can go, there's an equilibrium, state equilibrium at each point in the engine if that temperature is not changing. So we got stuff blowing through there at an incredible rate, but we have an equilibrium because the amount of mass going in equals the amount of mass going out. We've got the temperature of the hub, of the bearings in there have warmed up and they're not going to get any hotter, all those things. It's the same thing for your car. Cruising down the freeway at 80 miles an hour, if you do that long enough, there's going to be no changes. All the temperatures everywhere in the exhaust manifold, the radiator, they're all staying the same. If you slow down, you get into another equilibrium state. Things are going to cool off. And you go through all sorts of transient states from the time the transient states are those when it's warming up. Now, we got enough trouble dealing with things in equilibrium. We're not going to deal with transients because it just complicates things. We have enough trouble doing this equilibrium. But if you can get an equilibrium state, it's not too hard to conceptualize. You know, they're going to go through different states to get there. If you really need to study the transient states, that's really what the car manufacturers spend probably these days. They know how to make the car go fast, but how to make it so that the emissions, you don't end up with unburned fuel in the exhaust during startup is really one of their biggest headaches. That's their, not so much headache, the biggest challenge. How do you not have pollution at startup when everything's cold? They give them like 30 seconds of startup time, and then they have to be within emissions control limits, and that's a challenge. You learn a lot about things when you're doing that, the transient states, but we have enough trouble with steady state, so that's what we'll be doing. That's what we'll be doing mostly. So, the state of a simple compressible system. When we say compressible, we're talking gases. Liquids don't compress very well. If you know two independent intensive properties, density and temperature, pressure and temperature, that's enough. Probably the third thing is what fluid are we talking about? Is it steam or is it air? So if you know any two properties plus whatever the material is that you're dealing with, you know everything else. Because if you have two of those properties, all the other properties are going to. You could have a certain pressure at different temperatures, and you're going to have different properties. But if you have that pressure at a known temperature, everything else will be the same. It'll follow from that. Anytime you have that temperature and that pressure, you're going to have the same specific volume, the same density upside down. You'll have the same entropy. You'll have the same enthalpy. You'll have the same internal energy. And we're going to basically deal with two worlds. One is the ideal gas world, and the other one is phase change world. And and in our systems, it does matter. If you go underwater, you get different pressures and things. We're going to ignore gravity, or there's things you can do. All this stuff, surface tension can affect things. You get kinetic energy in motion that can cause pressure at the inlet of a jet. We'll kind of ignore that stuff. I mean, that does matter. If the jet's moving through the air coming at it will create an inlet pressure. But we're just going to look at stuff like, okay, this is what the inlet pressure is. There's ways to figure that out. But we're going to simplify things a bit, and we're just talking about the things related to the heat and so forth. So now that we've defined what a state is, which probably won't make sense until you start doing homework and more problems, so don't freak out if it's not making sense yet. A cycle is a series of processes that go between states. So if you have an engine, and say an Otto cycle, has a process, you get your intake all set up, and now you're going to compress it. You're doing a compression stroke. So that is a certain kind of process. It turns out it's an isentropic compression. We don't know what that is yet. We'll figure that out. But that means a certain thing, such that the end point is going to be at a certain volume, which it's going to have a certain pressure and a certain temperature and all the other stuff that goes with it. And then we light it off, and we're going to get, at the end of combustion, we're going to have a different temperature and a different pressure. And then we're going to have the power stroke, where that increased pressure from the increased temperature from burning the fuel expands as the piston moves. It's pushing on it, and that's another isentropic expansion. The combustion process will be a constant volume process, because the piston goes to the top and we light it off, and the piston's pretty much parked there while it burns. So we had an isentropic compression, and we have a constant volume combustion, and then we're going to have an isentropic expansion, and then back down to where we started. So those processes will be defined in terms of basically same temperature, or same pressure, or same volume, or same entropy, which we need to get through entropy before we talk about what that means. So we define these. Isothermal means you got the same temperature. Isobaric means same pressure. Isochoric or isometric, same size, same volume. So those are example of, and these will go between, there's a start at a particular it starts at a state and ends at a state, and how it gets between those states matters, but it ends, and then if you have a cycle, it wraps around and it goes back to the beginning, and it keeps going around. Otto cycle, diesel cycle, Brayton cycle, which is gas turbine, Rankine cycle, which is steam and refrigeration. They all have different definitions of what the processes are. But the processes always go between each states. The steady flow Steady flow is a case of like an open system boundary. You got the same amount of stuff coming in, going out, and it stays the same with time. That would be after the jet gets up to altitude and it's cruising for an hour at the same speed. That's steady. You're going to get, not immediately, but right when it comes up, give it a couple minutes, and now it's going to be in equilibrium and stays the same as steady flow process. And the way we define that, each point in the system, each part of each turbine blade stays at the same temperature over time. That's not changing. We have some forms of energy that the fluid can contain energy. There could be energy due to kinetic energy. We're not going to pay too much attention to that. It's real, and definitely in the inlet of a jet engine, the air coming in will generate an inlet pressure, turning the kinetic energy into a pressure. Deal with that in fluids, not so much in thermo. You can get a potential energy. This is what runs hydropower plants. That's another fluids kind of thing. We're not going to deal too much with how potential energy, you get into more detail on this and it starts to matter. There's chemical energy in the chemical bond strength. That's what makes fuels burn. What they do when they burn, they change from a hydrocarbon to the hydrogen goes to oxygen, with oxygen becomes water. The carbon goes with oxygen to become CO2. And in the process of doing that, they break apart bonds and they come back together, and the molecules vibrate, and that vibration is what we call temperature. It's higher energy. It's an energy state. If I put my hand on the tabletop, it feels cold. The molecules in my hand have net energy. They're transmitting to the molecules that are going a little slower on the tabletop. So this is where fuel energy comes from. We'll talk about that a little bit. These two are really what we're dealing with. There's work energy due to pressure times volume. If you have a pressure and a specific volume, that's the specific amount of work that it took to get it to that state. And then there's the internal energy that's related to temperature with mass and C sub V. I think this is actually maybe a little bit wrong. We can talk in terms of specific work per kilogram, kilojoule per kilogram of work that got done. And I kind of mix up. Usually if I'm using the lowercase, I'm talking about specific property. So volume per kilogram. I should have had a large D here because this has an M. This is the total internal energy. If I divide the mass through here, it'd have a little u, and it would be specific internal energy. But the concept is we've got work and we've got heat, and they're all bundled together. We'll use them kind of bundled together. And mostly what thermodynamics is going to deal with is these bottom two. How do we capture it? How do we convert it into, how do we convert this into that? That's really what it comes down to. Okay, where are we? Oh yeah, it's about time. Let's call it good for today.
He asked me, you said it would be tomorrow? On mine, it says on the 30th. It says on the 30th,
so,
which is Wednesday, right?
Yeah,
I'm
so
just-
if it says 30th, we'll call it the 30th, and yeah.
Okay.
Homework will usually be due, I've scheduled a chapter to be done, and then there's a day to talk about it, and then it turns in. If I'm behind on my lecture, then that day will slip. But in theory, we'll be done with the chapter, a day for questions, and then boom.
Okay. Thanks, Professor. Have a good night. See you tomorrow.
Yep.